Welcome, I'm Vincent Koch, and today I'm going to be talking about precision prompting, tuning LLM performance through algorithmic optimization. I'm a lead AI researcher in developer relations here at Comet. A little bit about me. I like to tinker, teach, write, and share about artificial intelligence. Outside of my role at Comet, I also hold academic positions in teaching, and in the past have been at roles such as Microsoft and worked at large organizations like Qantas. I also, in my free time, like to write a lot around technology and artificial intelligence at places like Towards Data Science and Forbes. And as you can see on the right-hand side, there's me, I don't know, some 15, 16 years ago trying VR goggles for the absolute first time. And as with any new technology or with anything new, the first time it can be a little wonky, it can be a little jonky. In this case, there was a warning saying, don't use for more than 5 minutes. I used it for an hour and was profusely sick following. But since then, VR has become so accessible, right? This was a really early development version, which later became the Oculus products, which later became the Meta Quest. As you can see, I'm also working with wearables and other types of hardware technology when it comes to AI and electronics as well. And a lot of this is quite important in today's reality when we talk about LLMs and we talk about techniques around language models and techniques around artificial intelligence and how do we optimize these systems. And a little bit about how I'm going to talk about this is going to be the same sort of concept of like, things that can be a little jonky, can be a little weird. The research is still sort of making its way out there. However, there are some exciting things that I think are going to be really worth your time for me to sort of unpack that a little bit. But before I get started, a quick forward-looking statement. Some elements of this presentation is going to have some concepts and features that are still under research and development within Comet. Some capabilities are very experimental, very beta, in some cases pending peer-reviewed publication. They're not fully supported for public production use, and they're shared for information and exploratory purposes only. But please don't be discouraged by this. It's very much a case to, it's a warning label, unfortunately, I have to slap on some of this stuff because literally what you're seeing and some of the stuff I'm going to be talking about today and some of the results very much within the last day or two that we've just been able to pull together just in time for Comet convergence. Now, speaking a little bit about language models and how we like to optimize them and how we like to work with them. If we keep it quite simple, we really have an input to a model and we have an output, which is the result that comes out of that model. I mean, obviously model can be anything, can be AI, could be ML, but in our purposes, let's think about large language models. Now, a lot of times we look at these models, we tend to think that the box in the middle is the key component as to what we're going to be optimizing. But actually, there's more to than just fine-tuning the actual large language model itself. I mean, from a model perspective, there's obviously model selection. We have a plethora of models available out there in different shapes and sizes, different quantizations, for example, different providers giving us different types of inference as well. So from a model perspective, even in that space, just before we touch fine tuning, there's a huge selection process that we can go through. But when we talk about the input that comes into a model, there is the system prompt itself, which is the instructions that we give to the model. There's sometimes a few short examples. So these are helping the model ground itself through some learned examples to say, hey, these are some examples I want you to sort of take. And based on these examples, can you please provide the next following output? There's hyperparameters. And when we think about hyperparameters, there could be things like temperature, top P, and various other parts of the language model that we can sort of potentially tune. And then lastly, there's a whole concept around tool use. And tool use is quite, not relatively new, but it's something that's quite emerging. When we think about agentic uses around large language models, we tend to think a system prompt followed by some tool or tools. Obviously, in complex multi-agent architecture, there could be multitude of tools that you can use. So how do we know the right tool is given to the right agent? How many tools can be given to an agent at a given time? So there are some concepts around sort of even just the architecture around the tool use component that's obviously become more prominent thanks to things like MCP in the short little while. And these are some elements that we could potentially work with when it comes to what goes into a model that's going to lead to an outcome, which is the result. And this goes beyond just the fine-tuning process. Now, if we want to get closer to this process, right? If we think about a traditional process flow, you as an engineer, for example, or you as someone writing a prompt would tell an AI model to behave in a certain way, it would yield a certain result. You'll then go through some evaluation process. Let's just go simple. We're going to use gut feel. You're telling this model to extract some data out of a medical report that's been scanned in. Maybe it's going to use the image. It's going to then evaluate that output. And then based on evaluation, you're going to do some sort of optimization flow. You're going to be like, hey, actually, it was able to detect this part of the text or was able to do these things, but these other parts were not so good. So I'm going to give it some little bit more instructions on what to do, maybe the style of the output or the length of the output or some examples of how to work with it. And when we work with these models and we do these prompting processes, we tend to do this sort of in an intuitive way. For those of you that have been maybe working with these models running prompts, it starts to become semi-intuitive, like you just kind of do this process. But really, the issue stems from is the fact that this process is kind of hard to iterate on in scale, right? Like you can't just go purely off your gut feel. Even if we had the eval space, the optimization part takes a lot of time, a lot of trial and error, a lot of figuring out what's working, what's not working, and sort of getting to the bottom of that. So kind of stepping back a little bit, why do we think we need to optimize prompts? And I'm going to say prompts, but we can also call that agents as well. So they could be multiple prompts and tools that kind of come together. Well, if we think about prompt engineering as a space, as I mentioned, it's not easily repeatable or scalable in itself. You're bound by individuals, you're bound by the experimentation that essentially has to go on from a human perspective, writing those prompts. We also tend to find that variation across models themselves could lead to certain performance degradation. So for example, a technique that you've tried or certain combination of words to get one outcome with one particular type of model may change going into another model. And this is not just models across different model AI labs, but it's also models across different model families or even within iterations within a given model itself. So for example, if there's a variation of an OpenAI model, certain training rounds later on may change the expected behavior of a given prompt itself. We also find that optimization as a process itself may also unlock things like not just the obvious like performance, but could reduce cost if we can kind of simplify down the token usage. We could create something that's a little bit more reliable as well from an output perspective. Then we also have the added complexity, as I mentioned, when you're starting to have systems that have multiple prompts working together, or you have tools and agents in the mix. So this is not just one single thing working on itself, providing an output, but when you start to multitude this together. So if you take a use case for, say, a customer support system at a large enterprise, they may have multitude of different AI agents that take care of these different tasks. The prompts all kind of stack together. So just optimizing in silo could be quite tricky process and quite hard to do. So we need to sort of take this compounding factor into place, and we see that actually optimization as a problem itself is potentially going to yield some result, given that it's quite hard to manage this just on a human level alone. So one of the things we want to start thinking about is like, how do we move away from that static LLM input? So that's like that input that I'm showing you here on the left-hand side. How do we move away from this just being a static input? Now, we've already got cases like people putting in context and information thanks to things like RAG around the user and their preferences and the situation, right? So we're kind of used to this dynamic approach to prompting, but how do we kind of take that a step further? So we know static prompts themselves are going to be fragile. They're going to be tightly coupled to model behavior. So that model, that version, that model family is going to be a concern, right? You're also going to lack that feedback loop. As I mentioned, this loop here. So you're essentially, in this case, without the evaluations and a structured approach to optimization, you don't have, it's like kind of driving without the instruments, right? So you're driving your car down a highway with the fog on, you got your fog lights on, but you just have no sense of direction. You have no sense of speed, right? So this kind of process without the feedback loop is like, you've got a kind of general idea of the direction you're heading in, but you're not sure if you're going to overshoot it or you're going to run into any kind of trouble, right? And optimization, essentially that process of optimization is going to help us kind of close that loop. And optimization only really works thanks to evaluation, right? We're not going to be able to get to that step of optimization if we don't know if the output result is actually good or bad. So the process of evaluation and optimization are kind of quite tightly coupled together. And lastly, one of the key interesting parts around creating a more dynamic approach to an input to an LLM, both hyperparameter, both the prompt and the examples, is it's going to enable us to do things like, for example, prompt migration. What happens when a new model candidate comes out? Can we quickly test, evaluate, tune this prompt and its examples? And if it yields a better result, be it better quality, less cost, whatever those factors may be, could we switch? And this kind of starts to bring us into this world of like automatic tuning or optimization as a service, which I'm going to touch on just a little bit towards the end of the talk. So one of the things that we've been working on, as I mentioned in the background, is called Opik Optimize SDK. This is essentially a new open source public beta. It runs as an SDK. It's baked into both the product, but it's a standalone package that you run and install that you can run these various optimizers. So I'm going to talk through some of these different techniques that we can use to optimize prompts and agents, but also what we're calling optimizers. And these different types of optimizers or algorithms or different approaches, as we like to call them, are essentially baked into this Opik Optimize SDK. And what we've tried to do is to try and automate this process and try and simplify this process as much as possible so you can take an existing agent, prompt, and help potentially tune that process and optimize it as much as possible to get the best outcome dependent on the evaluations that you're looking at. So some of the screenshots you're seeing there, some of the beta features that we've got on the left-hand side, for example, within Opik, we're launching like an agent optimization dashboard where you can see the optimization runs. And on the right-hand side is an example of, for example, a DSPY agentic architecture using a simple React and a tool. And that's been optimized. And we can see that the architecture there and how the system is able to kind of see into that. So with this process, what we're hoping to do is to help close that loop and automate that process of optimization. So we can already do things like evaluation inside of the open source Comet platform, Comet Opik platform, and then how do we take it from there to the evaluation step? So essentially that process we're calling evaluation in the loop or evaluation in the loop based optimization. So we could blindly optimize, but really once we've got the evaluations, we can optimize. Since the models and AI application can be tracked by a platform like Opik, the traces then go back into the results. We can then reevaluate that, and that whole process becomes an automated flow of some description. At least the data is flowing in one direction. We can start to see, is it getting better? Is it worse? And we can kind of start to create this continual process that's tied around the evaluation itself. Now, I'm not going to spend a great deal of time on evaluation. There's a number of different methods around how we can evaluate large language models and the results. And that's already baked into the products like we have with Opik. But what I want to talk about is the Opik Optimize SDK, which really takes the output from these models and these evaluations and helps you really take in and tune them as much as possible. So there's a number of various approaches and different algorithms we can actually use to optimize. And there's going to be 4 that I'm going to be talking about today. And these 4 work in very different ways. I'm going to talk about both how the underlying methodology around it sort of comes together, but also what we've done to sort of package that up and turn it into what we call an optimizer. And these are different types of optimizers that are available within the Opik optimization SDK that you can actually use to tune a given prompt. So the first one is we're calling few shot examples, which is more about picking the winning combinations. There's a process around meta prompting, which is using LLMs themselves to generate better prompts. There's a very famous MePro algorithm, which is used by DSPY and is focused around prompt templates and what they call DSPY signatures. And something which is a bit more on the novel side, a little bit different, is more evolutionary or genetic algorithms, which will essentially mutate prompts over time in order to sort of get different candidates and different styles. What I'm going to do is walk you through all 4 of these and talk about the differences and how they operate, how they function, and what kind of results we expected to see. Then we'll go through a comparison of all 4 of those in a very kind of meta way, and then some early results that we're seeing from some test data sets when we try to optimize prompts against them and some of the outcomes that we're seeing. So the first one is few shot examples. And as we know with any prompt, if we've got a candidate data set, a golden data set, we know that, okay, in a given case where a customer asks for A, we know we want to give them B, right? And what we can do is we can compile this data set into a set of examples. Now, the issue is going to be is like you might have 300, 400, 1,000, 20,000 examples to work with. How do we know which set of examples in which order are the most optimum? It's not just a case of what count of examples, but which combination of those examples we think is going to yield the best result. So in this case, few shot examples can be optimized in a very sort of simplistic manner just by randomly sorting through them and testing them in different combinations. In this case, we've created an optimizer in our SDK, which uses a Bayesian optimizer library called Optuna, which is a hyperparameter tuning library. And what it's doing, it's using a probabilistic approach to find the optimum mix of examples to bake in the right order, in the right combination that's going to yield the best results. So the graph that you're seeing, or the chart that you're seeing on the right-hand side, if you go from left to right, is each iteration of this optimizer running. So iteration 1, iteration 2, iteration 3, and then up, down, left to right is these are the different data set examples. So you can see it selected these ones down here. They're dark blue. The accuracy wasn't so good. So then it shuffled around and kept trying. And you can see here when it got to the yellow, it found sort of like a really good combination. And then you can start to see it starts to converge by mixing some of the ones that it did find and didn't find and test some different things. In this case, this optimizer works more like a bit of a random grid search in a way. It kind of picks a couple of different options and sort of starts to run with it. But we find that the results from this, it's quite good. And the reason why it's quite good is because we're giving a model through the prompt and through the instructions, hey, here's 5 examples that we think best describe this entire data set. Because we've run optimizations, we've run evaluations on different combinations. We think that this 5 or this 4 or this 3 in a certain order is able to best explain the output that we're looking for. And this happens without having to change the system prompt whatsoever. We're just purely taking the examples and we're feeding them in directly into the model. So once we've done that process, we can get some examples. But another example of optimization is this process known as meta prompting. So meta prompting, there's a couple of papers on this process, is effectively telling LLM, this is the problem I have. Think about it. How else would you act, say a prompt engineer, use your chain of thought process and come up with a better prompt? And you might have seen this in different tools where it's got, hey, I'm going to write a prompt and can you make it a little magic tool? Can you make it a little bit better or easier to work with? Now, this process kind of flips the head on the process by actually making the LLM the actual optimizer in this case. So you're telling the LLM to improve or rewrite its own prompts. And this loop will generate a new prompt, scored and then ranked. We iterate through it and we kind of create this self-reflective process. In the top right-hand side, you can see a comparison of a before and after. This is provided out of an OpenAI cookbook on meta prompting. They've got like a really simple example of how the process works, and you can kind of see a bit of an uplift. And the bottom right is taken out of a paper called Meta Prompting for AI Systems. You can see a slightly more complex process where the initial task is defined, which is then taken to that meta prompt LLM. It creates a meta prompt. That generated prompt then gets fed back in, and it creates this recursive process. So one of the interesting things that you can do with meta prompting is we can take the output of one meta prompt and feed into another chain and go, hey, this was the output. Can you make this prompt better? Now, some of the things that we've done in sort of making this slightly different is we kind of created this parent-child concept where in each round, a meta prompter would essentially generate maybe 4 or 5 or 6 really different examples. Each one would get evaluated, and then the best one will be kind of taken to the next round. The other thing we've also done in this case is where there's a metric defined, let's say an LLM as a judge or hallucination metric, we would tell the meta prompter, hey, this is the metric we're optimizing for. This is the history of the scores that we got. This is where we started. This is where it's going. And these are some of the prompts that we used in the past. So one of the differences that we've tried and we've seen some uplift in the results is actually feeding in each round of meta prompting into the next, but kind of in a cascading way. And we found that it's able to actually kind of really work well. We also find that reasoning models, when combined with this aspect, also give a slight edge because it's able to sort of like decipher potentially between the variations and sort of handle that complexity in the prompt a little bit better. But this essentially is just purely using an LLM to create another set of prompt or variations of prompts. Now onto the MiPro algorithm. As I mentioned, MiPro is a little bit more sophisticated. It's an algorithm that is using more what we call like a structured prompt programming. So for those of you that are similar with quite used to DSPY or understand the concepts around DSPY, it's kind of like this very modular way of sort of defining applications and LLM systems and not using a traditional approach. It has what's called as a sort of DSPY signature. You can kind of see this as more like as a compiled version of an AI system with a prompt and its tools and various aspects. And this process, what it does, it doesn't just mutate the prompt and make changes. It will reflect on the performance. It'll still use an LLM, but there is a bit more complexity around how it works. And one of the interesting things with DSPY is because it supports agents, we can actually give tools to these agents. So if you're doing RAG-based solution, an AI agent that uses like a RAG and connects to some data set, we can actually tune that process, or you can actually tune that agent with something like MiPro with DSPY, because it's able to actually run that agent and actually understand the complexity between the different tools and the actual system prompt itself, and actually sort of optimize that whole process in a whole. And that's what makes this one super unique, because it's able to really kind of take in that agentic approach to how do I solve that? Whereas the other ones are kind of a bit more focused on just the prompt itself or just the examples that go into the prompt. And lastly, the last one is what we call sort of evolutionary algorithms or generic algorithms. And these take a very different form of approach, and they sort of look at like evolutionary biology. And the idea is here we're using a Python library called Deep, which explores a large unconstrained prompt space. And what it does is it starts with a population of randomly generated prompts. And the randomly generated prompts at the start could be both a combination of the initial prompts, the initial prompt that you gave with some variation added to it through to an LLM or with some swapping of words, but also zero shotting it as well. So the beauty with this one is this algorithm, we've been able to add like a zero shot aspect to it, where essentially it will look at the data set and it will use an LLM to try and explain what is happening in that data set to construct the prompt. That gets added into the initial population. Then that population gets graded. It goes through a process of evaluation. And then the best ones that survive essentially kind of go into the next round. They then kind of have their own children in a way, but then there's mutations that occur, same as genetic mutations. And those mutations can include things like, for example, swapping out words, removing words from the prompt, putting other parts in, using LLM to shuffle things around. And that way we're kind of adding some variation. Other aspects of things that we've done in here as well is what we call LLM crossover, where we get an LLM to take these two prompts and combine them together. So this is where essentially two parents come together to have a child. That sort of concept is essentially borrowed in here. And we find that this takes a very different approach to creating an outcome, but it's kind of borrowing on the concept of meta prompting, but applying that to a genetic algorithm. So we're kind of using this concept of, can an LLM create some outputs? But in this case, we're using a genetic algorithm, but parts of this input into the genetic algorithm are essentially generated by another LLM. So we bring all these four together, when we bring all these four methodologies or algorithms together, they are quite different in their nature. Right? So when we take the few shot example, it's very probabilistic in nature, it's templatized, it's very stable, and it kind of creates a very efficient output. Semi-quick-ish, but it's kind of very reliable, very repeatable, because we know we're always going to get a result, right? With the few shot example, we're going to give it 100 data points. We know we're going to get 5 or 6 examples at the end. We're going to reach some conclusion, right? MePro, on the other hand, is a bit more structured, more interpretable, slightly more complex as an algorithm. However, that makes it really good for things like agents, like I explained, just given the way that its algorithm and its architecture actually performs. Meta prompting is more kind of LLM self-generated rather than LLM-guided. It's very much an early stage. It's a bit more simple. It's easy to comprehend and understand what is going on, but you're at the mercy of the large language model entirely to create the good outcome, the good data set, the good prompt that you're looking for. And then lastly, the genetic or evolutionary approach is a very different strategy altogether. And here we're actually exploring a very large prompt space. We're exploring very different combination by adding a huge degree of randomness and variability into it. So here there's going to be a bit more diversity, there's going to be a bit more exploration, but there is a chance we can find a potentially quite a good winning combination that maybe the other methodologies may not have. So in combination, all these optimizers work in different ways. They have different strengths and weaknesses. They have different cost constraints and time and energy required to actually compute. Some could take 30 minutes to 20 minutes if it's a large data set, and some could just be a couple of minutes to seconds, right? So we find that there's going to be a large variation between them, and that's going to give you some great ways to work with it. Other things that we haven't yet tested is maybe combining these together into different chains or rounds. For example, if you use the meta prompt to create your, or MePro to create your initial prompt, and then you use a few shot to create your examples, then you go through the genetic approach to then further tune that prompt itself, maybe that's going to yield some even better examples, right? So here we haven't quite explored this combination of these factors together and these different optimizers together, but there's nothing stopping you from sort of experimenting by chaining them together for a given use case. Now, some of the early results that we're seeing, and this is like totally hot off the press, I'm going to say that it has not been fully published, fully verified, very much demo purposes only. There is some heavy subsampling happening here as well in the data set. We're using GPT-4o Mini, running those optimizers essentially in a controlled environment over a number of iterations. So on the left, you've got RagBench data set. On the middle, you've got ARC. And on the right, you've got GSM 8K. Slightly different data sets, focus on different problems. And you can see that different optimizers are starting from an initial point, which is kind of low-ish, And the score we're looking at, the metric we're looking at is Levenshtein ratio, which essentially is looking at the embedding space to see how close it is to the answer. And here we see over time, it's going through different rounds, and you can see the winning candidates for each one denoted by the stars. Now, one of the things you're going to see that's quite interesting with all three of these is that different optimizers winning and performing quite differently across different data sets. And there could be a number of factors for this, right? Could be the problem space, could be the way the data sets are structured. And this is still areas that we're still exploring. Other factors that we also want to look into is how does these different data set and optimizers perform across different model families, reasoning, non-reasoning, different AI labs, and seeing if there's variation between those as well. And some early results have shown that in some cases there is some variation just given to the training data and how these models already perform in certain scenarios, that the optimization process may or may not yield as good as of a result in one model versus another. And this is still research that we're sort of looking into, a space that we're still exploring, and we'll be sort of publishing more of this as we go through. But the reality here is that different optimizers and different approaches are going to yield different results. There's not one magic bullet that we're seeing is going to solve a lot of these issues. I think the one that's coming closest to it at the moment is the few shot approach. But obviously that comes at a cost, right? Large few shot examples fed into a system prompt for highly complex use cases could create large token usage and may not be possible in some given scenarios. So based on that, you may have to sort of trade off up and down around the different approaches that you are going to be using when it comes to your optimization strategy. Now, let's say you've optimized everything, you've kind of gone through that process. A term that I quite like at the moment is this concept called prompt baking. Essentially, think of this as like your model registry in machine learning, but when it comes to instructions and LLMs. So in prompt baking, we take this optimized high performance prompt and we freeze it, right? So we create this like reusable versioned asset in a very compiled, deployable process way. So it could be a config file, it could be something that you can deploy. It has the tools, it has the hyperparameters. And in this case, we can now take this and we can treat this as like a production ready process. And over time, we can monitor how the evals are going, and we can keep running an optimization loop in the background. And if we find that there's some drift occurring, or we find that there's a better candidate model or there's a better candidate prompt, we can essentially swap these out, right? So very much similar in a machine learning space when you have a model registry where you would sort of register your model, you'd version them, and you'd run an experiment. We can take that exact same concept and we can apply that to large language models and AI agents in a very similar manner. Another great use case that we're starting to see others are publishing and talking about as well is that this is great for a model or agent migration process. So imagine you're taking a model or a prompt that you've used with one model, say with an OpenAI GPT, and you want to test that on Claude or you want to test that on Mistral. You'll be able to shift that prompt and tune it, or that agent, and you'll be able to optimize it for that given use case or that task. We can also tune or optimize agents around different ecosystems or tools. So imagine you've got multiple tools. How do we test the current multiple tools? Which tool is going to give us the best outcome in a given task or a given problem with a given data set? So again, this combination of the tool as a parameter that goes fed into the alongside the prompt and the data set as well is going to be quite an interesting exploration as well. And lastly, reusing existing prompts within potentially reduced impact to performance. So there's a case that we'll be able to sort of keep an eye out on how things are, and you're not going to be able to lose the work that you've done, saying really optimizing heavily for one model and then shifting to another one and seeing that it's slightly completely different, or you've got to kind of start from scratch. So at least you can use some of the learnings and the starting point there and sort of transfer that across to potentially other types of models or model families. Some anti-patterns and pitfalls to watch out for. This is based on some early observations and some of the research. There is a risk of overfitting to a given evaluator. So if you're using an LLM as a judge, you're using one LLM to kind of create the evaluation metric for you, where an LLM judges the output through another system prompt, you're at the risk of tuning your prompt against whatever that evaluator is. Ways to overcome this: you can add a level of randomness, you can add a level of human evaluation into this. You can also do things like look at other things like how different is this prompt? You know, if it's not that wildly different, I'm not going to shift, right? I'm just going to keep an eye on it. So keep that in mind. You're probably at the mercy of your metrics when it comes to this. So in some cases, multiple LLM metrics could help you, multiple evaluation metrics around your LLM could potentially help you and safeguard you against this. A token savings is not always, linked to semantic correctness. So it's not just about measuring accuracy. Just because something is less doesn't mean that it's going to be more correct or less correct. I think the aspects around latency and speed and cost and token usage are going to be intrinsically linked to accuracy and hallucination and some of these other factors, but also in the same way, they are going to be independent variables that you have to watch out for. If you over optimize for one, you may come at a sacrifice of another. So understanding the relationship between those in your given task and use case or your agent is going to be quite critical. Optimize often, I mean, experiment many all the time, don't stop, and avoid prompt drift. So now when we can measure these things and we can optimize them and we can experiment with them, we can essentially start to monitor for things like prompt drift, and seeing if your prompt is shifting a lot over time based on a data set, right? If we're starting to see the optimization process is quite wildly different each time, or we're starting to see different patterns in the few shots that have been fed in, what's causing this? Is there a shift in something that I'm not seeing based on the usage? Again, this creates another whole avenue for us of like exploration and understanding of observability around our AI applications that previously may or may not have been easily possible just purely looking at the inputs, right? The over reliance on the LLM as a judge without calibration, as I mentioned, look at feeding and human evaluation, look at other types of calibrations around that process to avoid sort of like overcompensating. And lastly, when we start to talk about the future of prompt optimization, so I've spoken about different optimizers, I've spoken about different approaches and techniques and what we've been working on as like a first cut of this, but optimizers as a service or what we call online prompt optimization could be a possibility. Imagine a case where you've got enough data around the usage of a system for a given cohort of users or a given other system that talks to an agent. Is it possible that that agent would get its own version of a prompt that's better tuned for its use case, like an A, B, or C kind of scenario? We could also look at agent and tool optimization. And what I mean by that is not just tuning one prompt or agent, but what happens where you have an AI system where there's like a few tools, a few agents, a few prompts? How do we actually collectively optimize it as a whole rather than as an independent prompt at a time? Multiple factors at once, again, things like cost, latency, token usage could potentially be combined to come up with a strategy. We have been testing things like, for example, increase in accuracy, but I want a decrease in tokens that are used in the prompt. So I want a simpler prompt that's going to yield a better accuracy. And that's kind of a policy or a trade-off that I can sort of do and test with. I could also use this to find best candidate models. So think about a case where there's a minimum accuracy threshold that we want to reach. And based on that minimum accuracy threshold, pick the best model for me based on inference cost, access, and also maybe the size of the model. So I want something really small, high powered, and can be move quite fast because I've got an agent for a specific task that isn't as complex as it needs to be. So based on that, I can find the best combination of model and best combination of prompt that's going to suit that given task for that given agent or that given AI system at that time. So I've talked a lot about agent optimization and prompt optimization processes. We talked through sort of some of the work that's been going on behind the scenes with Opik and our SDK. I hope you get a chance to try out the public beta, download it and take it for a spin yourself. In the meantime, I welcome any questions on here, and you're welcome to reach out to me directly if you have any further questions or wish to ask anything around this space. Again, this is a space that's continually evolving. We're doing a lot of work around sort of the research aspect and some of the findings that we're finding. And myself personally, some of the other aspects around the different models, the different optimizers and how they're behaving, there will be some follow-on materials that we will be publishing over time. Thank you so much, everyone. I welcome questions. Thank you.